FFT. We also looked at a few other variants of this because the fast Fourier transform is a trade-off between time resolution and frequency resolution, and also data storage for that matter. Sorry. So we did also investigate this Stockwell transform. That's a modified form of the Fourier transform with a Gaussian convolute convolved with a Gaussian term, Gaussian weighting factor. But it also requires a lot of computational memory, so it does have its limitations. So looking back at some of our actual research now, this is one that we did a while ago, but we're also revisiting it again now, looking at the sounds made by bees. For the acoustic signals, they are typically between 20 and 500 hertz, or 20 and 500 repetitions a second, and vibrations made by the bees that also shake the hive up to 3000 hertz. And the particular focus of our first phase was to try and detect whether a hive had a healthy queen in it or not. So the hive may have had a queen that died or was just not thriving, or it may have had a healthy queen. So the queen is vital to the colony because she's the only reproductive female, and worker bees in the height of summer, when they're most active, they only live for about 40 days. So if the queen dies, that can be an absolute disaster for the hive. It can mean the colony will die out very quickly. So we were trying to see if we could distinguish between queen right, where they had a healthy queen hives, and queenless hives where they didn't. And expert beekeepers, so that's just my washing machine physics cycle. Expert beekeepers could claim that they could hear the difference in the sounds that the bees made. So we wondered if we could do that automatically by electronic monitoring. That's a bit of review. I'll share these slides so that you can look at these at your. But that's some previous work on bee acoustics, and other people had more recently had looked at whether bees were about to swarm based on acoustic signals as well. That's something that we're interested in as well. We're trying to see if we can do that. Okay, so we looked at 2 hives that had a healthy queen in, and then we also looked at 2 hives located nearby where the queen had been taken out after doing initial control measurements. So we did control measure, or our colleagues did some control measurements for a few days, and then took the queen out of 2 of the hives, kept the queen in the other 2. So here we can compare it's a short-term Fourier transform, so it's the Fourier transform over a limited time window between a queen right hive, so that one has a healthy queen in, and this one doesn't. So I think you can see there's a bit of a difference in the profile of the peaks here between the 2 hives. The one with the healthy queen on the left, the one without the healthy queen on the right. And we looked at spectrograms as well. So a spectrogram has time going along the horizontal axis, frequency going up the vertical axis, and then the color or the intensity of the shading indicates how much energy there is in that frequency time bin, if you like, that particular frequency band at that particular time. And so the reds and the yellows mean high intensity, the pale blues low intensity, or the very dark blues low intensity. So again, you can see some quite marked differences here between the hive that didn't have a healthy queen from the one that did have a healthy queen. So possibly the bees are a bit more agitated there in the queenless hive. We also looked at the spectral density, as it's called, of the power. So effectively the power in the signal between a queenless and queen right hive, and we found that there were more occasions where the queenless hive had particularly strong spikes in the density, power spectral density. So although this the results were a little bit mixed. We did find evidence of some of three of the signals that earlier researchers had reported just by conventional means. And we did find evidence of differences between the queen-right and queen-less hives. But we did also apply a self-organizing map of form a neural network. The results from that were a little bit disappointing. We're recently been just looking at this data again and using more recent machine learning techniques such as the LSTM, the long short-term memory type of neural network, and also various other classification algorithms. And those are showing much more promise in distinguishing between the queen-right and queen-less hives automatically. But that's work that's still in progress. So the second phase of our project was to try and devise a smart hive that could be done at low cost. There have been companies produce smart hives allowing continuous electronic monitoring, but they tend to be very expensive. So a small hobby beekeeper or a relatively poor farmer that might be interested in monitoring health of bees on his farm wouldn't be able to afford those. So we were looking at ways in which we could produce a smart hive at relatively low cost. I think our ballpark cost figure was about 100 UK pounds. So that would be 10,000, I think. So multiplied by 100, 10,000 rupees. Still not, I admit that's not cheap, but it might be affordable by medium-sized farmers, but not by poorer ones. So we were looking at things that we'd be interested in monitoring, microphones to monitor the bee sounds, the temperature both inside and outside the hive. Healthy bees are quite good at regulating the hive temperature. They manage to keep it relatively constant, even through northern hemisphere, well, temperate northern hemisphere winters. The mass or weight of the hive to indicate whether it was gaining or losing weight. That's indicative of whether the hive's thriving in terms of the number of bees, also in terms of honey production, and also indicates things about whether the bees have swarmed and so on. I would note that also temperature is also a good indicator of when the hive is likely to swarm. The temperature will tend to rise significantly in the days immediately prior to a swarm. So if we notice a rise in the hive temperature, there is a good chance that the hive may swarm, but that's something we're trying to investigate more quantitatively. Bees don't particularly like damp weather, particularly rain. So monitoring internal and external humidity could be useful. Internal humidity to make sure it's not getting too sticky inside the hive. Monitoring wind speed and direction, that could also affect bee productivity in terms of how easy they find it to fly and so on. Rainfall, both because bees don't like flying in the rain, and also if we had a notable hive mass gain, if it was a flat roofed hive as some are, then this mass gain might be due to heavy recent rainfall, or at least partially due to that. We also put some gas sensors in, or at least one type of gas sensor in. Ideally, we'd like to be able to detect the natural pheromones that bees produce, because that might be indicative of whether they're healthy or stressed. And also things like airborne pollutants, like vehicle fumes and so on. Are they having a detrimental effect on the bees? Ideally, we'd like to be able to monitor the hive using computer vision, both externally to see bees coming and going. We have done some work on that. But also internally. Now, inside the beehive, it's pretty dark. I suppose you could light it artificially, but that might be disruptive to the bees. But we could use instead different bands of electromagnetic radiation, for example, infrared or ultraviolet cameras that might be able to detect the bees moving inside the hive as well. Now, there are issues with data storage and data transfer. Um,